found the joke funny last time.
You found it and funny this time, and so by induction, you will keep finding it funny. All right, so a quick announcement. This is the third lecture of the day. I will hopefully get the right one. This is supposed to be the lecture on induction. For those of you who are seniors, there is a meeting at 12:30, followed by a meeting at 1. For those of you who are not seniors, forget about that. But everyone is welcome to the monthly Math Stats dinner, which is going to be tonight around 5:30 in Mission. The other announcements is Kayla in particular is a little bit sad that you guys are in a room and I am in a room without any natural sunlight. And so she decided to try to help cheer up the place. And so we have two little pictures just so that the people who are watching this who didn't make class today, this is Elsa. Elsa, very good. And this is
a boat?
Sure. It might be the boat from the Lego movie, I'm not entirely sure. It also gives me some idea of how far I should go with the swivel and stay in the range so that I don't go too far off. All right, so what I want to do today is I want to do mathematical induction. There's the standard theory of it. I know most of you have seen it before, but I want to just go through it one more time. And then I just want to do a lot of examples. So I've chosen a couple of my favorite problems over the years that have a lot of good themes in them. And then I've chosen at least one problem that I don't know. And then we'll just continue from there to see what we're going to do the next day. So we'll probably do a little bit more induction on Wednesday. We'll probably do maybe some pigeonhole principle, maybe arithmetic mean, geometric mean. Right now, the homework assignments are not going to be too interesting because if I give you something, we've only done one proof technique, it's kind of clear how to attack it. But just because you know how to attack it does not mean the induction is easy. Induction is much easier when you know the answer you're trying to prove. Okay? And there is a beautiful website called the OEIS, the Online Encyclopedia of Integer Sequences, where you can put in a sequence of numbers and it will tell you, as I mentioned last time, every place it knows where it occurs. And if you're trying to prove things by induction, it will actually give you, here's the sequence, here's the formula for the nth term. And now you have something to try. Okay, so induction. So we start off with the base case. And so in the base case, show some statement P1 is true. All right, so I have some statement, and P1 is going to be that when I plug in n equals 1, it's true. Instead of doing n equals 1, what might I do? N equals 0, and that already is worth an M&M. Okay, so I might do n equals 0. It doesn't really matter if I start at 0 or 1. The next one is the inductive step. If Pn is true, then Pn plus 1 is true. That is much harder. And so the problem here is we need to show that whenever Pn is true, Pn plus 1 is true. We get to assume Pn is true. And if we can prove these two things, this then implies Pn is always true. And the proof is the following. I know P1. I know P1 implies P2. So what can I conclude? P2. But I now go back to this step and I now plug in n equals 2. When P2 is true, I know that implies P3. Therefore, what can I conclude? So therefore, P3 is true. I'm running out of space. P3 is true. Dot, 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 dot. Right, I will assume that this is enough rigor for this class as to why induction works. Right. I am required by law to do which example now?
The sum of all the numbers.
I have to do the sum of all numbers, okay? So example 0 plus 1 plus n is n plus 1 over 2. Right? I think there's at least one overlap between here and the previous class, so you do not need to use induction to prove this. You could actually write the numbers from 0 to n backwards. And if you do that, then you have 0 plus n is n, 1 plus n minus 1 is n, 2 plus n minus 1 is n. I must have gotten it wrong. 2 plus...
It's n plus 1 that's...
It's right. So I'll just do it here. N plus n minus 1 plus dot 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 plus 0. And then each vertical sum is equal to n. I have n plus 1 such sums. So twice the sum has to be n times n plus 1. So the sum is just n plus 1 over 2. So this is how you can do it without doing it by induction. All right. Sadly, we weren't that clever. Amazing. We somehow just didn't see it. So we're going to try to prove this by induction. So the first thing is P0 true? Does 0 equal 0, 0 plus 1 over 2? Yes, after extensive computations, we have verified this. When you try to prove things by induction, sometimes it's not a bad idea to do a couple of cases, small values of n, just to get a sense of what's going on. So do P0, P1, P2, P3, P4, do a couple of them. And after a while we say, hey, they're all right. I'm beginning to feel confident. I will conjecture that it holds for all n. And now we want to prove it holds in general. So now, so this was the base case. Now the inductive step. So we assume Pn. And we must prove Pn plus 1. And so of course, this is the statement that I'm calling Pn. So when you're doing all problems like this, you somehow have to work into the problem somehow that you know Pn is true on your way to proving that Pn plus 1 is true. Well, if I look at the statement Pn plus 1, I want to study 0 plus 1 plus 2 plus n plus n plus 1. And when I write it like this, it becomes really clear, I hope, how I can use Pn. So Pn is talking about the sum of the first n integers. Do we see a sum of the first n integers here? Yes. Over here, by the inductive assumption, this is n plus 1 over 2 plus n plus 1. And now we get to do one of my favorite proof techniques. So it's a little bit presumptuous maybe to call this here a proof technique. How would I add these two numbers? Multiply by 2 over 2, common denominators. What I'm really doing is I'm multiplying by 1. Multiplying by 1 is one of the most powerful things we can do in mathematics. What is the other big thing? Adding 0. And one of my professors at Yale, Peter Jones, once remarked, the logarithm of 1 is 0. There's really only one thing you can do in mathematics. We will multiply by 2 over 2, and now we get n plus 1, 2, and we get n plus 2. So I can write that as n plus 1 times n plus 2 over 2. And to just really belabor a point, I'll write this as n plus 1 over 2, which is what I needed to show. And that finishes the proof. OK. Any questions about this? What made this problem easy? Yes? Yeah, you've got a huge M&M debt. You've got to work this off. Yeah.
2 now. This is the third.
OK.
We knew the formula before we...
That's right. So instead of looking at the sum of the first powers, what should we look at? Sum of the squares, fine. 0 squared plus 1 squared plus n squared. And what does that equal? Anybody remember? I believe that's the answer. One way you can check is you put in a couple of small values of n and see if it works. I think this is right. The main thing is the first term has to look like n cubed over 3. Why does the leading term have to look like n cubed over 3? Yes?
Because that's kind of like you were roughly estimated. That's what you'd be getting. Because you have kind of roughly n terms, and the upper bound is n squared.
But why n cubed over 3? I want a little bit more. Well, if this is a polynomial in n, I claim it's got to look like n cubed.
Well, one way to do it is to estimate that sum of the interval.
Good.
From 0 to n.
So I go from 0 to n, and I'm not going to worry about should I go from 0 to n or 0 to n plus 1. I have x squared dx, and this should be n cubed over 3. So the leading term should look like n cubed over 3 if it's a polynomial. What's nice is if you don't know what the formula is, you can actually just plug in a couple of values of n. And if you assume it's a polynomial, you can do Lagrangian interpolation. I have a polynomial. I know its value for a couple of n. I can then figure out what it is. So if I gave you the sum of the cubes, Well, it should be a polynomial now of degree 4. I know the leading term should be n to the 4th over 4. Is there a constant term? So here the constant term is 0, here the constant term is 0. Is the constant term always 0? Yes, why? I'm sorry?
0 and 0. So yeah.
If I take 0 terms, the sum is always 0. So when n equals 0, I always have a sum of 0, so my answer here has to have 0 constant term. So we actually know the extreme terms, and it's the middle ones we have to figure out. And so with some work, we could guess what it is for n cubed and higher. If I give you n to the 3, if I give you, I don't know, let's choose a completely non-random number. Could you find a formula for this by brute force? Yes. Pleasantly? No. There's better ways to find the formulas for this than using induction. You can do this by induction, but this is going to become extremely tedious. And you can start to ask, do you need an exact formula or do you only need an approximate formula? And if I need an approximate formula, it'll be n to the 332 over 332. For large n, that's going to be a really good approximation. All right, so this is the standard first problem that you're supposed to do in induction. Anybody know the second problem? Any thoughts as to what the second one is? So the first one is adding all the integers. The next one is adding the odd integers. So let's see. So example. So let's just start gathering some data. The sum of the first odd integer is, okay? The sum of the first 2. Okay. If you haven't seen this before, what's the pattern? Square, what am I squaring? The number of terms. 1 plus 3 plus 5 is, okay, is this a proof? No, just because you've checked it a couple of times does not mean it's a proof. So this is one of my favorite examples. Aside. 12 over 24, lowest terms. I'm sorry? 1/2. All right. 16 over 64. 19 over 95. 1/5. 49 over 98. 1/2. I disagree with one of your answers. Which one do I disagree with? Which one is wrong? 12 over 24, correct. What is 12 over 24? 1/4. Because 49 over 98, you cancel the 9s and you get 4/8, which reduces to 1/2. 19 over 95, you cancel the 9s and that's 1/5. 16 over 64, you cancel the 6s, you get 1/4. We've checked this 3 different times. That's more than enough data to be convinced that it should always hold. So the way you divide 2-digit numbers, if they have the same number on the anti-diagonal, is you just cancel the numbers. And so 12 over 24 should be 1/4. Okay? This is one of the most common mistakes people make in mathematics. Maybe not this particular calculation. Common Core hasn't been around that long yet. But the idea of checking a few cases and going from a few cases to it always holds. And there are a lot of patterns that start going off in a certain direction, but if you go further, they stop. So the question becomes, how would we prove this by induction? We now have a conjecture. So the conjecture is the sum of first n odds is n squared. So how would we prove this? Yes?
We check the base case, so now we just assume that it's true for n and see if
Sure.
n.
Base case is done. Inductive step. So 1 plus 3. Now we have to figure out how do we write the nth odd number. So how would we write the nth odd number?
So like
not quite. Close, yes.
2n minus 1. It's 4.
All right, so let's check. We're almost going to prove this by induction with an induction. If n equals 1, we get 1. If n equals 2, we get 3. If n equals 3, we get 5. This is going to be the nth odd number. Okay, so the inductive step, we know that this is equal to n squared. So now we study 1 plus 3 plus 2n minus 1 plus 2n plus 1. And what do we know about the sum of the first stuff? So it's n squared plus 2n plus 1. Sometimes life is just good, right? It's in the right order. It's screaming at you. N squared plus 2n plus 1. This is just n plus 1. Yes, the square is important. Okay. Do you want to do another standard or an unstandard problem? Unstandard. I need somebody who has not taken a class with me and I do not know well. All right. You have to be willing to show me your driver's license or some form of ID. Okay. I remember the first time doing this and being upset when I found out my students were born in the 80s. All right, yeah, well, I will make sure that the camera does not see this. Okay. Did you know that everybody's name is Emma? So everybody is actually named Emma. So I'm going to prove this. Let's see if we can get the camera to swivel. So now what we have to do, sometimes I apologize for the people in the video. All right. So we'll just erase this. It's easier than trying to get the camera to move. So I'm going to prove everybody is named Emma. I'm going to do this by induction. So all people have the same name. Okay? And the proof is as follows. So Pn is the statement, in a group of n, all have the same name. Base case, is P1 true? Yes or no? Yes. Yes. Why is P1 true? Yes, Emma? No, not you, Emma. Emma.
Oh, because Emma's Emma.
Emma's Emma. Well, we don't know right now that everybody's named Emma until we look at the driver's license or whatever. But we know in a group of just one person, does everybody in the group have the same name? Yes. Now we'll do the inductive step. Pn is true. Show Pn plus 1 is true. So sadly, Kayla is not here to do the drawing. Sorry, I shouldn't be adding people. Okay, so here's person 1, 2, 3, and n plus 1. How many people are in this group? N. What do you know about these n people? No, we do not know the name Emma. They all have the same name, right? Which Emma made that mistake? All right, be careful, Emma, okay? What about these people? They all have the same name, okay? But person 2 is in both groups. So everybody in the first group has the same name as person 2. Everybody in the last group has the same name as person 2. Therefore, everybody has the same name as person 2, which coincidentally happens to be Emma. So as 2 in both, all have the same name. What is wrong with this proof? Yes, Emma?
If they're just two people,
Mm-hmm.
then they don't overlap.
Good. So when I drew this in a very misleading way. I drew this for n large, right? But the problem is we may not have n to be large. If n equals 1, then here is the first group, here is the second group, and this is n equals 1, this is n plus 1 equals 2, and there's no overlap in that case. So that's the problem, is that this picture is quite misleading. And if you want to think about what's going on, one of the ways I like to view induction is I view induction almost as a staircase. And so with a staircase like that, we'll do it the old-fashioned way. So this is how I view induction. I view induction like a staircase. What's going on here is we're missing a step. And so when we're missing a step like this, we can't go from here to here. Now, once we know that in any group with 2 people, everybody has the same name, then it is the case that in any group with 3 people, they all have the same name. We just don't know that second step. How many of you have seen this proof before? Okay. There's lots of fun ways of doing this. They sometimes do it as all horses have the same color. And then this leads to the jokes in the future that, if this were not to be the case, that'd be a horse of a different color, which doesn't exist by the previous lemma, for those of you who remember the Wizard of Oz movie. The other fun variant I know about this is every integer is a perfect square. So all integers are perfect squares. Mm-hmm. Do you want to see proof that every integer is a perfect square? All right. So let's Pn be the sum of n squares is a square. Okay. Does anybody buy P of n? The sum of n squares is a perfect square. Anybody buy this? Is P1 true? Yes. If Pn, then Pn plus 1, well, a1 squared plus an squared plus an plus 1 squared. By induction, what do we know about this? It's a perfect square. If this is a perfect square, we can call this x squared plus an plus 1 squared. And what can we say about that? Perfect square. And again, it is the exact same fallacy as before. Right? The problem is, again, we don't have things that are true when we have a sum of 2 things. And that's another way of just exploring an interesting consequence of something like that. So you've got to be very careful. Frequently, you will have situations where the claim holds from some point onward, but there is a missing step. And this is the most common mistake people make in inductive arguments, is they somehow implicitly assume something about the AN that they're studying. Okay, any questions about these arguments so far? All right, the automatic swivel technology seems to no longer be swiveling, so we will go back to more primitive ways of doing it. I'm sorry? Okay, so I want to try to do some proofs by induction that you maybe have not seen before. And so I wrote down a couple of my favorite ones. And so let's see. OK, so here's one. So claim 133 divides 11 to the n plus 1 plus 12 to the 2n plus 1. Oh, 2n minus 1, sorry. That would be silly. OK. What do you think? Yes or no? So I'm hoping there's at least some skepticism, because I've just given you 2 false proofs by induction. But I haven't done any proofs yet. I'm just making a claim. What do you think? True or false? What can you do to get more confidence? Plug in some values. So when n equals, what's the first value of n we should take? 1. I would say in this case, thou shalt not use 0, because then you've got a 1 over, it's just not good. So take n equals 1. There's 133 divide 11 squared plus 12 to the 2 minus 1 is 12. So that's 121 plus 12 is? All right, what should we do next? 2. So now is 133 divide 11 cubed plus 12 to the 5th. 12 to the 3rd? Oh, yeah, I'm doing 2, thank you, 12 to the 3rd. So what does this equal? We can split up. I'm just curious first, what does this equal?
It equals 133 times k.
All right, 11 cubed plus 12. They're both cubed? Oh, that's nice. So it equals 3059. And now if we take 3059, what should we divide that by? Come on, this is obvious. What should we divide it by? 133, right? And we get 133 times 23 or 29? 23. 133 times 23. 2 data points. Is that enough to convince you? Good, I see a lot of skeptics. So the question is, how can we do the general case? How should we look at this? Yes?
We could just do modular arithmetic.
We could do modular arithmetic. So the question is, when we do modular arithmetic, how do we want to do the modular arithmetic? We somehow want to do things by induction, right? Why do we want to do things by induction? Bless you.
Theme of the day.
Theme of the day, it's all we know, right? It's our hammer. We're going to keep using this hammer. So how would we try to do this by induction, going from here to here? Yes?
You notice that 133 is equal to 11 times 12, so if you can show that your sum is equal, congruent to 0 in both mod 11 and mod 12, that should be good.
Okay.
No, they aren't. Oh, I can't multiply.
Yeah, I was going to say, because if this were the case when we looked over here, this is congruent to 0. When I look at it in mod 11, it's congruent to 1. Right. This is why the fundamental axiom is thou shalt not do algebra in public. No, I'm just as bad as anyone else. The advantage of being the professor is I can say, I deliberately made that mistake to illustrate a point. So how should we try to do this? We want to somehow do it by induction. And again, this is the first time I've taught a class like this at Williams. There's a lot of ways to do it. I can ramble through the proofs at warp speed. I don't think that's the best way to do this. I want to have discussions. I think you learn a lot from trying to view problems like this and approach them. Yes?
Well, can't you just if you assume that it works for n, and then you write it out for n plus 1, and then you modulo 11 to the n plus 1, and then modulo
All right.
12.
So assume 133 divides 11 to the n plus 1 plus 12 to the 2n minus 1. So now we consider 11 to the n plus 2 plus 12 to the 2n plus 1. And so we want to see, how is this different from what we had before? How can we get what we had?
Wouldn't it just be 12 to the 2n?
I'm sorry?
Wouldn't it just be 12 to the 2n since you're adding
No, because it's 2 times n. So it becomes 2 times n plus 1 becomes 2n plus 2 minus 1. Yes? And we might want to write this maybe as 11 to the n plus 1 plus 1 plus 12 to the 2n minus 1 plus 2. Because again, it's not necessarily clear what's the best way to look at this.
Well, if you mod by 11 to the n plus 1 first, then you get 11 plus 12 to the 2n minus 1 plus 2, and then if you mod by 12 to the 2n minus 1, you get 11 plus 12 squared, which I think is mod 133.
Okay, so what you're trying to do is you're trying to break it up into the cases from before
No, I was just.
to see is it congruent to 0 mod 11? Is it? Didn't quite follow that. So when we look, we know 133 divides this expression. We want to somehow get that expression from this. Yes?
Can you subtract the previous one, and then the previous being 11 to the n plus 1 minus, and 12 to the 2n minus 1? Because that's, we know, is divisible by 133.
I can subtract that, but if I subtract that, I'm going to have, nothing is going to meet up with anything. So you're on the right track. Because if I just directly subtract this, I'll get 11 to the n plus 2 minus 11 to the n plus 1.
Can you divide that?
I could try to divide by it. If I try to do long division or something like this, I would expect like this to be like this mass exodus to the door. You're on the right track.
Could you perhaps express it as a product of 11 to the n plus 1 plus 12 to the 2n minus 1, and then subtract off some suggested cross term?
So we could subtract off some suggested cross term or something. So over here, I have an 11 to the n plus 1 plus 1. I have an 11 to the n plus 1. How could I get these to align? What could I multiply this by? I'm sorry, I think somebody said it. 11. So if I multiply this by 11 and subtract, I know this is divisible by 133. So if I subtract off 11 times that, if that remainder is divisible by 133, so is the original thing. So I can look at 11 to the n plus 2 plus 12 to the 2n minus 1 plus 2 minus 11 times 11 to the n plus 1 plus 12 to the 2n minus 1. And when I subtract, the 11s cancel perfectly. And I'm left with 12 to the 2n minus 1 plus 2 minus 12 to the 2n minus 1 times 11. I can factor out 12 to the 2n minus 1, and I get 12 squared, which is 144 minus 11. And not surprisingly, 144 minus 11 is 133. So it's 12 to the 2n minus 1 times 133. So this, I think, is a much harder induction problem than the other ones we've seen. And this is one of the reasons why I want to go through this problem. It's not at all clear how you should be using the given information. So in terms of writing an algorithm to solve inductive problems, going through the steps, it's not such a big deal, right? Show the base case is true. Use the base case and the assumption that Pn is true to then show that Pn plus 1 is true by finding Pn somehow in the expression for Pn plus 1 and using what you know. The difficulty is finding that expression that you know. How do I find something like this? Well, one idea was to take what we know and subtract it. And how many times can I subtract it? I can subtract it 11 times. Or I could have gone another way. I could have subtracted it 144 times and canceled this term. And then I should probably get something very similar, maybe with a negative sign now. So again, these are difficult problems to see how you would apply something like this. Okay. Any questions about this one? All right. Chessboard or dominoes?
Dominoes, it's solvable.
Okay. They're actually both the same. How many say chessboard? All right, we'll do chessboard. All right. So now we'll try to figure out why the tracking is not working. Okay. So here's the problem. Can you cover a 8 by 8 chessboard by the following pieces? If we delete the top right corner. Yes.
For the piece that you specified, does every one of those squares correlates with one square on the
Yes. So I have a 3 by 3, and I can spin this however I want. But all of these are 1 by 1 by 1. Those are 1 by 1. I have 3 of them. So what's your first way to tell, is this reasonable? A quick sanity check. Yes.
Well, so what I would do would be to make 2 by.
No, I don't want an algorithm. I want a sanity check. Yes, Emma?
Is 63 divided by
Yes. Is 63 a multiple of 3? Right? Is 63 a multiple of 3? Yes. There's a chance that it will work. Right? But I have, if you've seen Indiana Jones, you know, the first one where they removed 1, right? We removed 1. It's 63 squares because we removed the one in the top right corner. Yes. That one's gone. So there's at least a chance that this is doable. What do you think we should use?
Induction.
Induction. What the hell do we induct on here?
Powers of 2.
Powers of 2. Why powers of 2?
1 doesn't work.
1 doesn't work. If I try a 1 by 1 board, does it work? 1 by 1 board. Yes or no? No. Well, maybe, you know what? Maybe 1 by 1 doesn't work because you're being stupid. Right? This.
It does
Works,
work because
yeah,
if you
you're
delete the
moving
top
the
right
corner.
Oh, wait. Okay. It does work.
Could have been like a no way exclamation point.
It works. All right, so if 1 by 1 works, what should we try next?
2 by 2.
2 by 2. Does 2 by 2 work?
Yeah.
Now we're getting more excited. So by induction, what do you think about 3 by 3?
No.
we should look
Well, why does 3 by 3 not work? Yes.
Just count the number of squares that's left over.
Ah, so for 3 by 3, there's 8 squares. There's no way 3 by 3 can work. 3 by 3 board. No. Okay? Not going to work for 3 by 3. And this is because we have 8 squares. Not divisible by 3. What's really nice about this is this simple observation that we have to have a multiple of 3 number of squares means we don't even have to try to go through all the different cases of trying to put down these tiles. So what this is telling us is there's going to be a real danger in trying to prove things by induction because it's not going to be doable for all values, for all chessboards that are n by n. All right, continuing after our failure at 3 by 3, what should we try next? 4 by 4. Is 4 by 4 potentially possible?
Yeah.
Okay. So now we have to figure out, does 4 by 4 work? And so, you know, at some point it actually plays to just make the board. 1, 2, 3, 1, 2, 3. All right. And now we can start to try to put in all the different ways. Maybe I take these 3 tiles here, then these 3 tiles here. Would I want to do that? Why would I not want to do that? I'm stuck because of this. So I don't have that many choices. I can do these 3 tiles, I can do these 3 tiles, I can do those 3 tiles. So if I want to do these 3 tiles, that's my first possibility as this one big piece. What should I do next? Yes?
If those 3 kind of approximate, so it's like symmetrical.
Okay. So I could try these 3 over here. And now what do I do next? So I could take these 3 over here.
I found a way to do it. Yeah. Then you take one that goes like this. Like that.
And now these 3 over here, I can put in one like this as well. And now over here, I'm fine. So the idea is to try to go through this and see what can we glean. Notice that in the analysis, when we're trying to do the 4 by 4, we were actually breaking it up into 2 by 2 blocks. And in each of those blocks, we solved the problem with the missing corner. Does it matter if the corner that's missing is the upper right versus the bottom left? No. Thou shalt spin, right? Just move it around, it doesn't really matter. We then align them in such a way that the three missing corners over here all come together, and we can put this one new placeholding piece here. And then we know how to do this one by induction. So we can now do the 4x4. So we now have a way to make a giant tile like this. Right? So we can make this giant 4x4 tile that's missing a piece. Do you think we can do 5x5?
It's theoretically possible.
It's theoretically possible. 5 times 5 is 25, less 1 is 24. So I don't actually know if 5x5 is doable. Yes?
I think we can do any number such that if you subtract 2 and it's divisible by 3, then you can make it work. So 5.
So can we do 5x5?
Yes, because 5 minus 2 is 2.
All right, so one question is to see, is there a way to get a 5x5 to work? And so, if so, it's not going to be using something like this. Okay, there's going to be issues. But maybe there's another way to do it. So as a nice exercise, try to think, can you do 5x5? When you do math competitions, there are almost always problems involving the year. And the question is whether or not that actually matters. So you should always know, is the year prime? What's the next prime maybe after the year? Are there any special properties? Usually it doesn't really matter. But sometimes maybe it matters, is it an even or an odd number? What is it congruent to? Things along those lines. I'm sorry?
You can do 5x5.
You can do 5x5? Excellent. All right, so we've just been told that we can do a 5x5. And I assume it does not look anything like this?
No.
Okay. But, yes?
So, yeah, I have to figure out how to do 8x8.
Okay. So now that we can do the 4x4, what do we do? Yes? How do we do the 8x8?
So since you have the 4x4 piece,
Yes?
you know that you can take one of those 4x4 pieces to get in the top right.
Okay, good.
So that takes care of that much. And then, yeah, you take, like how you already have the one there, and then you take another one, you just rotate it around,
Yep.
and then another, yeah, do the same there, and then another 3-piece will fit in that missing slot.
So that's a very messily written description. All right. How should you do this in a non-messy way?
Induction.
Induction, right. If induction is the answer to the first n questions of the day, then by induction is the answer to the next question of the day. Right? So, you just now write this up formally using induction. And you can always do a 2n by a 2n. Now, the more general question of which boards are doable by this, that's a little bit harder. But at least at this point, we know we can do the original problem of 8x8. And this is just one of the advantages of having a chessboard that is a power cube. So again, this was a problem where the number 8, it actually mattered that 8 was 2 cubed. So this is in fact the second lecture in a row I've given today on the glory of 8 equaling 2 cubed. The other was Strassen's algorithm for the operations research class. I sadly forgot to connect that to my 389 class. Although 8 is 2 cubed and 9 is 3 squared, so maybe that's a connection. Okay, so we have time for one more inductive problem. And so this is another very, very standard problem. How many of you have seen, can you cover a 2 by n board with 2 by 1 tiles? And if so, how often? So again, here is my board. And here are my tiles. I can do it either this way or this way. So the first is, can you cover it? Yes. Give me a way to cover it. Vertical, 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 vertical. Okay. So the first question is not really that interesting.
Do you mean how many ways rather than how often?
Well, how often, how many ways? How many ways? So the question is, we want to figure out how many ways are there to cover it. So let's start counting. When n equals 1, how many ways are there? When n equals 2, how many ways are there?
2.
2. We can either go brr or brr. All right, now n equals 3.
3.
So we have something like this. How many ways are there?
3.
3. What are the 3 ways?
All this way.
All, okay, all vertical is 1.
Two, these 2 vertical, and then these 2.
2.
No.
All vertical is
The-
1.
the- These 2 horizontal and
2
these 2
horizontal and then a vertical, or vertical and then 2 horizontal. Okay. When n equals 4, there must be 4 ways. Because it's 1, 2, 3, 4. No. Okay, how many ways are there if it's 4?
5.
Oh, it's actually 5. So can you do 5? Can you do this by brute force? If you're patient enough? Yes. And if you continue, when you do n equals 5, you'll get 8. When you do n equals 6, you will get 13. And in fact, if I did n equals 0, what would it be? We won't worry about that. You might say maybe there's one way to do nothing. I don't know. But here, it should be clear that this is the Fibonacci numbers. So can we prove that this is going to be Fibonacci? Any thoughts as to how we would approach this? Induction. I deserve that. Yes.
Well, it should be too hard because Fibonacci itself is an inductively defined sequence.
So the Fibonacci's are, well, inductively or recursively defined sequence. So we want to find some way to define. So let's assume.
But can you ever do it by like, if you took like 2 off the board with like +1, then you could do 2 horizontals?
Yes.
Or you could-
Excellent. So assume if 2 by n have fn ways, we've got to be careful in terms of how we define the Fibonacci numbers. Where here, f1 is 1, f2 is 2. Okay? So I'm defining the Fibonacci numbers this way, where the sequence goes 1, 2, 3. Okay, I don't have 2 1s, I don't start with a 0. You've got to be careful. Do we want to use the letter F or do we want to use a different letter?
I think F's good.
Yeah.
I'm sorry?
Still like F.
We like F? Okay. Some people would sometimes use other letters. Absolutely fine to do it either way. You just have to be very careful about how things go. And so we know by induction. What I like about this problem is we're actually using a stronger form of induction than the normal one you see. And so now, assume Pn is true. So consider Pn plus 1. So if we're going to tile it, what are my possibilities for the first tile? Or the last tile? Maybe I'll do the last tile. Yes?
Vertical or horizontal?
It's vertical, or the last tile is horizontal. Okay, well if the last tile is horizontal, the only thing I can do up here is to just put a horizontal one as well. By induction, how many ways are there to tile this?
N.
I'm sorry?
P of N.
F of n. Right, P of n is the statement that the number of tilings is f of n. So by induction, I am assuming that Pn is true. How many ways are there to tile this?
Then minus 1.
Why?
Because you're taking up 2 bars at the end rather than just 1.
Okay. And are we done? Unfortunately, the induction that you bought is not strong enough. You didn't get the option package.
So yeah, you have to assume that it's also true.
So we
Even
have to
minus-
assume not that Pn is true, we have to assume Pm is true if m is less than or equal to n. This is often called strong induction. It's worth the extra cost. Yes?
But is it less than or equal to or just less?
No, because we want to, because the normal induction would be we would assume Pn is true, and now we want to prove Pn plus 1. In strong induction, we are assuming it is true for all m up to and including